Hello, everyone. Welcome to the new school year and welcome to this class. Uh, so this is a new class and it's a class on kind of advanced topics that are developing very rapidly in research. So we would all love feedback on what you think, what you'd like to talk about more or less than what we are talking about here. Um, This is also a new room and it has this screen here. So I'm gonna have to try to figure out what to do with this screen so it doesn't get in the way. But uh yeah, so I'd be happy to get started. Let me make sure my screen is shared. Yeah. Yes, I am recording. Thank you for reminding me though, because I might not be recording, so you might want to remind me every time. Um so yeah, let's get started. At any time, feel free to raise your hand and ask questions or make comments or whatever. We tried to keep the size of the class manageable so that we can have discussions and everything. Cool. So this is the obligatory slide that I need to show at the very beginning. I promise this is the only slide, but we all use language models all the time. So we use ChatGPT, Google Search, Copilot Cursor for code completion, coding agents like Codex, OpenHands, specialized apps. So no matter which industry you're in, people are probably using language models in that industry. So there's Harvey for legal or Abridge for medical, et cetera, et cetera. So for a language model, I'm coming into this assuming that almost everybody in this class or everybody in this class has either taken a natural language processing class or a deep learning class. So I'm assuming that most people know all of this stuff already, but I want to get us all on the same kind of page with respect to, the notation that we're going to be using and other stuff, the terminology that we're going to be using. So a lot of this class is going to be an overview of that. So for a language model, what we talk about when we are talking about a language model is a model that assigns probabilities to sequences of tokens. Um, this could be conditioned on, something else like an image or something, but mostly we're going to be talking about in output where it's a sequence of tokens, either in natural language or code or something like that. And so we're calculating the probability of X for a sequence where the sequence is X1, X2, all the way up to XL. And the most common method, it's not the only method we're going to talk about, but it's the method we're going to be talking about most of the time, is autoregressive models. And so autoregressive models decompose like this, where we have the probability of the next token given the previous token. So we have the P of the whole sequence is the probability of the first token, and then the probability of the second token given the first token, probability of third given the previous ones, et cetera, et cetera. There are some counterexamples to this. So the one major counterexample that we're going to talk about in this class is diffusion models. And diffusion models are a very different type of model with a very different inference algorithm. And so from the point of view of inference, they're interesting in that way, but that's going to be like one class out of all of them. So unless I mentioned that we're doing something different, assume that we're talking about autoregressive models. So we can look at some unconditioned completions. So I took a small-ish model, Quen3 1.7b base, and generated some completions from the BOS token, the beginning of sentence token. Actually, Quen doesn't have a beginning of sentence token, so I generated it from the end of sentence token, but it's more or less the same. And I split these into high probability, medium probability, and low probability sequences out of the 100 sequences that I sampled. Anybody, oh, and sorry, one additional thing is when you do inference, you need to decide when to stop. And so I stopped when I got a period or an end of line. So any idea what the highest probability token sequences are if you sample from nothing? Yeah.
The token the.
This is a token sequence, not a token. So it's not just the token the. Yeah. Any ideas?
This is the base, okay, this is the base one, I was gonna
It's
say
the base.
Show happy to help or something like that.
Yeah,
Usually instruct on.
it's not an instruct tune model, no. Any ideas?
Is it something in Chinese?
Some of them are in Chinese, but it's not these are not the highest probability ones. Okay, so the highest probability ones are 3 period, 4 period, and zero parentheses and then end of line symbol. So yeah, these are relatively high probability. This is the log probability, so you can see minus 4.22 means if you sampled quite a few times, you would get a bunch of these. What about middle probability? This is from the Quen model, if people are familiar with Quen. This might have been a little bit unlucky, might be a little bit of an artifact, but I got a lot of code. So these were kind of the middle probability ones out of the 100s that I sampled. Also a lot of math. And then the lowest probability ones, which are still high probability because we're sampling 100 and picking the lowest probability ones, were mostly Chinese, actually. So lots of Chinese. I don't know if this is good Chinese or bad Chinese. Political Chinese? Okay, well, you could guess what Quen was trading at. Cool. But that's actually not what we do most of the time we use a language model, right? Instead, what we want is we want to do something that's useful. And usually something that's useful means conditioning on something else. And so when we do this, basically we want to condition on the previous sequence and generate the next sequence. This is also written where the input sequence is X and the output sequence is Y. And so in this case, we will treat the first part that we're conditioning on as the prefix or the query. And the second part is the completion or response that we want to generate from this. So mathematically, what this essentially means is if we have the autoregressive decomposition, that means we can just omit the first tokens in the product. So we were conditioning on all of the previous tokens typically when we generate the output, but now we can just omit them. We calculate this autoregressive decomposition. So for my prompt here, for the prefix, I use the best thing about Carnegie Mellon University is, and any idea what the highest probability tokens are? What everybody would be saying is the best thing about CMU.
Computer science something?
Computer science. That's kind of a weird sentence. So the best thing about about Carnegie Mellon University is computer science. Maybe that's just slang. The faculty, that would be a pretty good one. And thank you for flattering me. You get 2 bonus points. The community. Okay. We got its diversity. So, and that it's a community. So that it's a community is kind of faint praise, I think, but maybe okay. Middle probability, we get ones that are a little bit longer. Its location in the vibrant community it has built, that there's always something else to learn, that it gives you the ability to take your education to the next level. So these are, a little bit longer, but maybe still pretty typical sentences. And then if we look at the lowest ones out of the ones I sampled, it's focus on the interdisciplinary approach with students majoring in computer science, mathematics, and engineering, the community that you get with it, so many people doing so many different things, and not just its academics and research and engineering, computer science, and business. It's the amazing out of the ordinary experiences your students create in the classroom. So, all pretty reasonable things. Computer science made its appearance, I guess. What's something you notice about these other than, just the text content? The length, yeah, exactly. And why are the shorter ones higher probability?
When you multiply something with less than one, it's always even less than it. Sorry.
Yeah, so when you multiply something by less than one, it's always less than the thing that you start off with. So like you notice here that we're, making many multiplications. They're all probabilities, so they need to be less than one. And so they will get shorter and shorter. Notably, I'm using the Quen base model. And how do we train a base model? I'll get to in a few seconds and then, or in a few slides and then get back to this. So um, in terms of modeling, again, this is a bit of review. I'm assuming that everybody here has looked at transformers and probably even implemented transformers in one of your previous classes. But basically, we have transformer models. And unlike the transformer model in the original paper, this is a fully, it's a decoder only model. And, um, and what that means is if you look at the original paper, you had like an encoder and then you had a non-masked attention and you had cross attention and other things like this. But now in the decoder only models, essentially we have an embedding process, positional embeddings, masked multi-head attention. So you're masking to not attend to future tokens or the current, not attend to future tokens, layer norm, and then the feed forward network, and then layer norm again, a linear layer, and a prediction. So this is, I guess this is probably familiar to everyone, given that you've taken the prerequisites for the course. So there's lots of other options, and I think we will talk about some of the other options as well. Like there are mixture of experts models, which don't necessarily do full mixed feed forward layers or things like that. There's also recurrent neural networks or state space models such as Mamba. I don't necessarily assume that you know of all of these, or at least are like super familiar with all of them, but we will cover these in more detail in future classes. But one thing that's super salient when we're doing inference is the modeling cost. And so I wanted to talk about transformers mostly from the point of view of modeling cost. And so there are two components that take the majority of the modeling costs that we deal with, which is that they have self-attention. And self-attention is costly, but it's also quadratic in sequence length for some components in the attention. And then the feed forward layers, which are wide and heavy. And we also have N layers, where N can be a relatively large number in our very big models. So here's a quick quiz. Who thinks that in modern large language models, self-attention takes more time or is more costly than feed-forward networks? Anybody think self-attention is more costly? Anybody think feed-forward networks are more costly? Anyone think this was a trick question? Okay, it was. So I'll talk about that in a second. But thank you for volunteering to answer anyway. I appreciate it. So I'd like to talk a little bit about the number of flops that it takes to calculate a transformer model per layer. And specifically, I'm going to focus on the grouped query attention transformer, which is a transformer that is used pretty widely nowadays. And basically what grouped query attention does is we can put it on the board. So in the typical multi-head attention in transformers, basically what we do is we have some big vectors that are the hidden states that go into the attention function. And then we split them into heads, and then each head kind of attends to the each query of the head attends to the keys of the other head, and then you use that to weight the values. In grouped query attention, you essentially create groups of the key vectors and value vectors. And you you attend like this to save memory. And so what this entails is self-attention. First, you calculate the projection of the queries, and this basically costs all of the compute because you're calculating this for every head. But for the key and value projections, you calculate less because you're grouping them together. And then you have the actual attention calculation. And for all of these, if L is the length of the sequence and D is the dimensionality of the entire vector, and DH is the dimensionality of the head, you are calculating this over the entire vector, but you're also doing a quadratic attention calculation because each position the query is attending to the keys, or you're multiplying the queries in the keys. So this is the quadratic component, and then you have the output projection here. But so you can split this into a quadratic component that grows quadratically as the sequence length gets longer. And then you have this component over here, and this component over here, which is basically linear in the sequence length. You can see by looking it out. And then if you look at the feed-forward network, the flops per layer is basically the dimensionality of the underlying embedding times the dimensionality of the feed-forward network. And you calculate that for, like, if you're using the swig-glue, you have a gating function, and then you have an up projection and down projection. So basically, this is entirely linear in the sequence length. So let's look at an example of how big these values are for each of the for the Llama 3.1 series. And I just picked the Llama 3.1 series because it has one example of like a very big dense model, 405B. This architecture is used pretty widely in a bunch of other model classes as well. But we can see we have like 32 layers and 80 layers and 126 layers. The hidden size is like 4,000, 8,000, and 16,000. The attention heads are kind of proportional to this. In grouped query attention, they always have 8 over all of them in the Llama 3.1 series. And then the MLP size is approximately 3.5 times the hidden size. So one other thing I forgot to put in this table is that the maximum context length is 128K. So because the maximum context length is 128K, the largest L would become, in these cases, is 128K. So let's look at the flops that we spend on each component versus context length. Basically, it looks like this. And you can see that as the context length gets longer, the flops increase super linearly with the context length. And so we can see the total flops scale quadratically with the context, at least if you look in big O notation. And when the context length is shorter, like 1,000 is still not a super short context length. The MLP part is the green part here. This dominates the cost of the computation because it's 3.5 times larger than the other parts. And then the linear part of attention, the projection, costs a lot of money. And actually multiplying the attention vectors together doesn't cost a whole lot. But as you get up to larger context lengths, actually the quadratic part of attention starts to dominate. And so this becomes a problem if you want to scale attention to, much longer lengths. And so practically, what does this mean for inference? It means that it's expensive. So this is a lot of flops, and it also means that you start to become limited as you have very long sequences that you're dealing with. Great. So this is the base, and this is kind of like the ideal setting where we're only calculating flops and we're not worrying about like whether we can use all of the flops that our processor or chip allows us to use efficiently. And I'm going to talk a little bit more about that in a second. But are there any questions here so far? Or comments or discussion? Yeah.
You mentioned the LLP size is 3.5 times the hidden
Mhm.
layer. Why?
Yeah, it's a good question. I think there's two parts to this. The first part to this is just people have experimented a bit around it, and this seems to work relatively well in terms of the like compute accuracy trade-off. It should be larger than the hidden size, and the reason why it should be larger than the hidden size is this allows you to like combine learn combination features. Um, Another reason why is there's, and I'm not going to be able to give this super accurately off the top of my head, but there's like this tends to be a like exponent of 2. And this tends to not be an exponent of 2, but when you actually go in and calculate the like utilization of the GPU, having this be like an X 3.5 is good for GPU utilization based on threads. But yeah, sorry, that's I'll have to go back and look up the like actual justification for that to say that more accurately. Yeah.
Just try to work on a number of flops calculation. So what is multiplied by 2?
Oh, yeah, great question. Why are all of these things multiplied by 2? And the reason why is a matrix multiply is a multiplication and in addition. So you multiply by the weight and then you add it to the sum. Yeah.
These are two operations.
Yes, exactly. Yeah. Cool. Anything else? Okay. Cool. So anyway, this is really really expensive, and so we need to find ways to, we're willing to pay the cost if this gives us a really good model, but we need to find the way to utilize these flops as efficiently as possible. Cool. So another big theme of this class is going to be, how we can make inference efficient. And to make inference efficient, you need to know a lot about hardware. And typically, we use different varieties of hardware for inference. What we don't use that often for larger models, but we still use for smaller models is CPUs. And CPUs are, general purpose compute, but they don't have a very high level of threading. And so because of this, they're not particularly good at the operations we need to do for neural networks. Then there are NVIDIA GPUs, and NVIDIA GPUs are kind of the gold standard of what everybody uses. There's also like AMD GPUs and other things like this, which are very good hardware, but not as well supported in the software ecosystem. So people don't use them quite as broadly. But with respect to NVIDIA GPUs, there are a variety of GPUs that people use. The typical ones are like A100, H100, B200. These are kind of server grade ones that, if you have lots of money, you you spend that money hiring these expensive GPUs or buying these GPUs. There's also cheaper kind of like non-server grade ones that people typically use for gaming or other applications. But these still are quite powerful and much better than using a CPU. There's also special purpose hardwares. So there's things like the Google TPUs, and Google TPUs are maybe the second most commonly used type of hardware for this sort of training, just because Google uses them a lot and they're available on Google Cloud. These are optimized. So GPUs, originally started for gaming. So they weren't originally made for training, AI models. Um, Now, arguably, they are made specifically for training AI models, just because that's how NVIDIA makes all their money. But TPUs were created from the ground up for doing this, and they have things like very large memory, very fast interconnect. And then there's also other special purpose hardware like Cerebras and Grok and other things like this. Um, one thing actually is a little bit of a logistics thing for this class. So in this class, um, we're going to want to run some inference on GPUs, and we're going to try to provide this for you. We have maybe three main ways. One is if you already have access to inference compute, or to compute that you can use for inference, you can use that. So like, for example, if you're an LTI and you have access to the Babel cluster or something like that, you're welcome to use that for the class. We're also going to provide AWS credits. AWS credits can get you some amount of compute, but uh, I will warn you in advance that it takes a relatively long time for us between when we apply for them and when you actually get it. So having a backup plan is good. It's not our fault, it's AWS's fault. But and thank you, if anybody's listening, thank you, AWS, for giving us free credits. I'm not blaming you for anything, but and then also, we've had a lot of success with Google Colab Pro, which costs a little bit of money, but it's very convenient for running experiments. It's like $9.99 a month. And actually, I think you can get it for free for students. So that's another one we recommend. Another thing that you may be interested in, I don't necessarily recommend that you do this, for this class project, but there's also a lot of, sorry, if I press escape, if I press escape, this happens, but there's also recently a lot of GPU like marketplaces. So just to give an example, so if I wanted to actually go out and do training or serve something myself in kind of a more like industrial setting, there's kind of two varieties of GPU service that I would suggest. Ones that I have used are Modal and RunPod. And Modal and RunPod are particularly good for like if you want to spin up a bunch of GPUs quickly, or you want to have like serverless GPUs or things like this. And so one of the assignments in this class is going to be build an inference server. And then if I actually wanted to build an inference server and deploy it somewhere, what I would do is I would serve it here, and then I would use serverless endpoints. So like when somebody hit it, they would be able to do inference there. And then separately for things like training, there's also things like San Francisco Compute Company and Prime Intellect. And these are basically GPU marketplaces where you can like rent GPUs. And what they do is they have people who sell GPUs or rent out GPUs, and then people who want to rent GPUs. And so they have a market. So you can actually see the actually, I don't see it right now, but like Prime Intellect has like a stock price, like a stock ticker, but for GPU prices. So it's kind of, yeah, here. So this is like the price for an H100, and you can actually see it go up and down like the stock market. So it's kind of fun. Cool. Sorry, that's a little bit of a divergence, but compute is going to be important. So just to summarize, you can use existing compute if you have it. We will try to get you AWS credits, and you can use Google Colab for free, Google Colab Pro for free. So those are my suggestions for this class. Actually, TAs, could you take a note that we need to do that. So thank you. Cool. Any questions here? Okay, great. So next, I'd like to go into training. We are not going to do very much training, if at all. None of our assignments require training because this is a class on inference. It's not a class on training. But you might nonetheless be interested in doing this, and it's particularly salient for me to like explain the most important differences between training and inference. And so usually we train on large corpora of text and then, maybe do pre-training on, all of the text on the internet and then do post-training or fine-tuning on instruction data. And recently, lots of reinforcement learning. So here the goal is to learn parameters such that the probability approximates the probability of the true distribution using maximum likelihood estimation. I assume everybody knows this and has done this in previous classes. And we want to maximize the log likelihood of whatever data we have. Importantly, and we do a forward pass, backward pass to compute gradients, and a parameter update where we have a learning rate. And practically, we process large batches of text with tensor operations using GPUs or whatever else. And so what this looks like is a little bit like this. So essentially, we have an embedding layer, and we step through each layer of the model until we get to the very end, and we predict the loss, and then we add the loss together, and we get a final loss for our entire data. So just to do that again, to contrast with the one I'm about to show for inference, it's like this. So big block, big block, big block, big block, big block, big block, and then finally predicting the outputs. So this is really important because it's very different from inference. And when you're doing training, if things go well, you can like completely saturate a GPU all the time, or get very high flop utilization. So what about inference? Inference, given a prompt X, we want to generate a continuation. There's two main approaches here. The first is drawing samples. So from the probability distribution, or from a probability distribution, we randomly draw samples from the model. The other one is search. And here, search instead is trying to argmax some score of the output. And this score may or may not be the probability. And in fact, in many cases, it's not the probability. And I'll explain why we would choose something other than the probability in a second. But going back to the diagram that I showed before, let's look at inference. So now we have smaller block, smaller block, smaller block, smaller block, smaller block. Predict a word, and now we're kind of walking through in an autoregressive fashion to do to calculate the outputs like this. And then we finally get to the end of sentence symbol here. So what do people notice or know about the difference between training and inference? Yeah.
You know that open beforehand, and so you can forward pass across all of them. But that's what inference you need to wait for.
Yeah, so great. I'll just repeat it. So training, all of the tokens beforehand, so you only need to make essentially one step through each layer, right? Here we had 3 in the prefix and then 3 tokens we generated, so we had to make 4 steps through each layer. We had the first 3 and then 1 and then 1 and then 1. And so we have a lot more steps. And this is a problem. The reason why it's a problem is because each step here essentially has a fixed cost in that we have to dispatch to our GPU, and then we need to wait for the GPU to finish processing. And both of those things can take time. And also we might not fully saturate our GPU because GPUs have many, many threads. and we might not be using all of the threads at the same time. So this is a big challenge in efficient inference. And it's something we'll be talking about for like a good portion of the class. How do we overcome this challenge? Cool. Yeah.
So when you generate new words, don't you update the previous existing one?
Oh, yeah. So great question. When we generate new words, don't we have to update the embedding of the previous words? And the answer is no. And the reason why we don't have to update the embedding of the previous words is because we're using masked attention. And so we're masking out all of the future inputs when we calculate the embeddings of the previous inputs, which means that the inputs at position 3 cannot depend on the word in position 4. And this is really important. The reason why it's important is clear if we go back all the way to the autoregressive decomposition. So you'll notice that when we generate the words, we're always conditioning only on the previous words. And the reason, or sorry, tokens, when we generate the next token, we're only conditioning on the previous tokens. We're not conditioning on future tokens because otherwise the chain rule of probability doesn't hold here and we can't calculate this. Also practically, it would be difficult to, there are practical difficulties with updating all the previous tokens. So that would be an issue. There is the one exception to this that we're going to talk about is diffusion models. In diffusion models, you actually do generate like not entirely left to right. You generate from like the whole thing at the same time. Yeah, it's related to the Markov assumption. So it's like, well, kind of. The Markov assumption is like assuming that some tokens far in the past are like not actually relevant, but we don't actually do that in transformer models typically. Yeah. Great question, though. Any other questions? Cool. So, okay. So now I'd like to talk about basic generation algorithms. And basically this class is kind of split into 3 parts. The first part is going to be more on basic generation algorithms. We often just call them generation algorithms or inference algorithms. But what I mean by this is essentially they're algorithms that in an autoregressive model are typically 1 token at a time, or maybe 1 token at a time while maintaining multiple hypotheses that we're searching over, like in beam search. And so a simplified view, this is the most simplified view of this, which is that we have a generation function that takes in a model and then has an input as a list of tokens, which would be our prefix. And then while we have not finished generation, and then we take the model and we calculate a probability, and then we somehow sample from this probability and append this to Y. And the model always takes in a prefix of the previous tokens in the next token. And in reality, we're not like appending tokens like this. We're appending to a tensor or something like this for efficiency, but this is a basic idea. And we'll cover many variants in the course, starting 2 classes from now, basically. But this is kind of the first several classes that we're going to talk about in the course. Should be familiar to everyone, I guess. So the next thing I'd like to talk about is something called meta generation. We coined this term, so it's not like a super standard term, I guess. It's in the survey paper that was in the reference for this course. But I think it's a reasonably good term. And basically what it means is it's a class of algorithms that generate token sequences more or less as a subroutine to the main algorithm. And so one most common example of this is a re-ranking algorithm. And there's many, many other examples, but this is the most common one, which is we have generate and re-rank. So we have the model that we're using to generate. We have a re-ranking model. And then we have the number of candidates that we are going to generate. And then we have the prefix. And so we generate that many candidates. We generate scores from the re-ranker. And then we return the candidate that has the highest score. So this is just one example. And again, we're going to cover many of these, of course. Any questions or everything okay?
Like,
Yeah.
say candidate, does that like wait till the EOS token is received, or like you start to re-rank in the middle of?
Oh yeah, that's a great question. So this is number one, this is like the simplest possible meta generation algorithm. There are also other ones that would do something more like this. But I didn't actually define done here. So I didn't define done as like Y has, hit the EOS token. In fact, when I generated from Quen to generate the examples here, I defined done as hitting the EOS token or the period token or the end of line token. So you can define it in other ways. And so you could also define it in a way which is like generate 5 tokens and then re-rank them or something like that too. Yeah. Cool. So another thing we're going to talk about is latent variables. And this is really important recently in particular, very big like focus in that a lot of people are paying attention to like O1 or R1 reasoning models and stuff. But the basic idea is sometimes we want to model things other than the actual answer that we're going to be showing to the user. And the most common variety of this is chain of thought. And so what this would mean is our input X would be something like how many years since the transformer paper was published. And then the latency would be now is 2025 and the transformer paper was published in 2017. 2025 minus 2017 equals 8. And then the output would be it has been 8 years since the transformer paper was published. And this is people have demonstrated that this is a really good way to improve the accuracy of models. And in particular, recently, people have been training models to do this. But latent variables pose a lot of issues with respect to inference. Notably, two are the most obvious ones. The first one is efficiency. So who uses like GPT-5? Or any of the other models? How long have you gotten it to think? Too long. Anybody over 5 minutes? Okay, that's pretty impressive. Anyone over 10 minutes? Okay. Cool. Okay. Yeah. So that's impressive. But that's an efficiency problem, right? Like you would like your answers as quickly as possible. And so if the model needs to think for 10 minutes before you can do that, then maybe that's an issue. So that's the first thing. The second thing is actually you don't really care about the latent variable a lot of the time, right? Like often you just want the answer. And in fact, GPT-5 doesn't show you the latent variable. It doesn't show you the full thinking process of the model. So, if you're not showing it to users anyway, you don't really care about it. Or as a model provider, you obviously don't care about it. So what you could do is you could also consider multiple chains of thought and then finally decide to find the output that is the best given multiple ways of deriving that output. So like you could solve a proof or you could solve a math problem in like 10 different ways and find the answer that's most common. And this is called self-consistency. And so there's a bunch of different varieties of this too. Okay. So another big topic that we're going to cover in this class is evaluation of inference outputs. And So we don't actually want high probability outputs most of the time. We want good outputs by some measure of good. And it's not necessarily the case that high probability outputs will be good. So there's a lot of ways you could define good. You could define good as human preference, being, what humans like the most. You could also define good by asking an LLM to grade the outputs in the same way that you ask humans to grade the outputs. So this is typically nowadays called LLM as a judge. You could also use deterministic metrics. So like if you're solving a math problem, there might be only one real answer. And so you could just check if the answer is equal to the correct answer. Also, these are less common nowadays, but there are deterministic metrics to evaluate generated text as well, like blue or rouge. If you're talking about reinforcement learning or talking to somebody who knows a lot about reinforcement learning, they'll often also call this a reward. And I will basically use these interchangeably, like an evaluation metric or a reward. They basically mean the same thing. It's just like how good your output is. So a really important concept, which everybody who is working on inference should know, but unfortunately not everybody working on inference knows, is the idea of search errors and model errors. And a search error is where the search algorithm failed to find the output that gives you the highest model score. And so if your model's a probabilistic model, the model score is a probability. And so basically what this means is when you ran whatever generation algorithm you were using, it did not find the highest scoring output. And so this could be, S could be the highest probability, or it could also be, the most consistent output, that thing with the highest marginal probability when you're marginalizing over chains of thought or something like this. So what this means is basically your search algorithm failed. If you're using an argmax search algorithm, it did not find the max. So if search errors are your problem, this can be mitigated by better inference algorithms. You can find a better search algorithm, and this will do a better job at finding the highest probability thing. So you might switch greedy search into beam search, or you might switch beam search into A-star search, or like some other search algorithm. The other thing is model errors. And model errors are basically when your model's score, S theta, is not a good output according to whatever evaluation metric you care about. And so what this means is you get a lower reward for your generated output than you get for when you actually, now that I look at this again, I don't like this. Sorry. This might be wrong. I might have to fix my slides. This is the first time I teach this class, so I might have lots of errors in my slides. I'll try to catch them, but if you catch them instead of me, that's very welcome as well. So basically here, what this means is so we define y hat is the highest scoring output. And then based on that, we have so what this means is whichever output is scored the highest by your model is not as good an output as the best output. So What this means is your model is misscoring the outputs, and it's basically assigning a higher score to bad outputs or outputs that are not ideal. And the reason why this is an important distinction is this can be mitigated by better model training or inference. And what I mean by this is probably the quote unquote correct way of solving this problem is by training your model better. Because your model is wrong, right? Your model is giving a low score to a good output and a high score to a bad output. So back when I was more strongly opinionated, I would actually say this should not be fixed by inference. This should be fixed by, coming up with a better scoring function by like better training your model or using some alternative decision criterion or something like that, using a different re-ranking. Now, I have seen enough people succeed at fixing these problems through inference that I also think it can be fixed through inference. So, but we need to think about what fixing this problem through inference means. It basically means breaking your inference algorithm to get a better output. So not intentionally not finding the highest scoring output so that you get a better output. So you just need to keep that in the back of your mind whenever you're doing like tweaks to your inference algorithm to get a better score. This is an important thing, and we can talk about it again when we talk about beam search or versus sampling and other stuff like that. Yes.
A high-level question about the goal of inference. The goal of inference to sample or to optimize. So am I interested? I have a probability distribution of outputs. If I want to sample many outputs or sample near the mode, or do I want the mode?
Yeah, that's a great question, and I actually provided two alternatives, right? To do argmax or to sample. I would say yeah, so it's a good question. I think typically we use it to refer to both. And they're two different varieties of inference. I understand if you come from statistics or something like that, there's probably a more strict definition, but I think it's used for both of them mostly. Yeah.
But if it's for sampling, then the first one doesn't feel like a search error, right? Because I wasn't trying to optimize them. I generated something, maybe.
Yeah, and actually this is particularly focused towards the case where you want to get a good output. And so people use sampling algorithms to get good outputs nowadays, largely because models tend to be broken. One thing I should point out is with the best language models that we have nowadays, people are sampling less and searching more. So like the best models, if you want to get them to do things like code generation or mathematical reasoning, very often people are using greedy search, which is not a great search algorithm, but it's still like much more likely to give a high probability sequence. And the reason why is because they fixed a lot of the search errors through model training. So they've like trained models to be really good at like actually generating good outputs. It used to be that this was a really bad idea. Like if you use greedy search, it would repeat itself over and over again. And in fact, next class, I'm going to show how to generate from GPT-2, and you're going to see greedy search completely fall apart on GPT-2, which is an old model. Maybe that I should mention that. But yeah, this is particularly focused on the case where you want good outputs, this discussion here. Yeah. Cool.
And so the amount of like search error you have and model error you have, does that vary on like how you're storing and what good means?
Yes, definitely. So like if you switch your scoring, so like the question was the amount of search error and model error that you have, does it depend on what your reward function is basically? And the answer is yes, definitely, because the reward, like for model errors, oh, actually that only applies to model errors because how you're defining good only shows up in model errors. If you look at the equations for search errors, it doesn't show anywhere. So the search errors are only defined by the model scores themselves. Yeah.
How can you know if a given error is like a search error or model? How do you distinguish?
Yeah, I mean, I gave you equations to distinguish between them, but like you can, how do you know if a search error exists? One way you can do that is come up with a better search algorithm and see if you can find a better hypothesis. And so if beam search is an example that we're going to talk about, and you can expand your beam and search more and see if you can find better hypotheses. And if you don't find any better hypotheses, it's not an existence proof. It's not a proof that your best hypothesis is the best ever, but it's, some evidence for it. If you do a star search, which we're going to talk about too, there you can actually prove that you found the optimal output. But a star search is not feasible in neural networks. Then for model errors, if you find many hypotheses and you can find at least one where this equation holds, then you have a model error. So you could output 100 hypotheses and you could try to find one where this equation holds. Great question. Cool. Okay. So I'd also like to talk about diversity versus quality, which is kind of like going into the same point. Like, what's our goal of searching, or what's our goal of doing inference? And so the first is if we do argmax search, if we search for things that maximize the probability, this will often give us lower diversity. And so, like, if we're only picking the top one, then we're not going to get any diversity at all in modulo like numerical instability due to GPU processing or something like this. But if we do an n-best search where we try to find the top n examples, sometimes they'll vary by like 1 token or something like that. And we're not going to get a whole lot of diversity in our outputs. In contrast, sampling gives high diversity and sometimes lower quality. And that, especially if we have a relatively good model with few model errors, typically the highest scoring one will be the best. So argmax search will give you the best results. But both are useful in different cases. Does anyone have an idea where we want to have more diversity for sampling? Yeah.
It's something like creative writing, like writing probably an essay where you want to be more expressive. So maybe something like that. Whereas if you're like predicting something which is more templatized like finance, you would want to do that.
Yeah, so that's a great point. The answer was something like creative writing. Arguably, yes, but what if you could come up with a really good evaluation metric for creativity and optimize it? Maybe you only need one output given a prompt. So if I say like, tell me a story about a fairy that really likes to do math. Maybe your argmax is good enough. So, but if you want the case where you show 10 different outputs to a writer and let them choose the one they like the best, then you obviously need some diversity in there. So yeah. I saw some other hands. Yeah. Okay. Yeah. Yeah.
Synthetic data set creation.
Synthetic data set creation. So you want to create data that like mimics a true data distribution. That's a great example. Another example might be reinforcement learning. So if you're like training a model and you want to sample lots of outputs, you want to make sure that you have enough outputs to represent the true like variety. And so there you'd want diversity as well. And we'll talk a bit more about that later. Cool. So this is the recap. We're approaching the end of the like actual content of this class, but we want outputs that give us good evaluation scores. We also might want low latency. So in terms of like you put in a prompt and you get the output pretty quickly. If you're a model provider like OpenAI or Anthropic, you might want high throughput because you're getting millions of people asking you queries. So you want it to be able to generate lots and lots of them. Possibly high diversity for model training or for showing different outputs to different users, things like that. And depending on the application, the priorities might vary. So it's very dependent on what specifically you're trying to do. So in this course, I'm just going to go through all of the topics that we're going to cover. So the first one is what we just did now. Next time, I'm going to talk a bit of probability review, and I'm actually going to mostly do Jupyter notebooks next time instead of slides and give some quick examples of each of the 3 topics we talked about. So talk about some probability background, some probability basics, generation algorithms. Oh, sorry, like a simple implementation of the transformer, generation algorithms, meta generation algorithms, and then inference. Efficiency. Then we're going to talk about common sampling methods, beam search and variance, intro to A-star and best first search, and other varieties of controlled generation. So this is going to be like kind of the generation section that we're going to be talking about. Next, we're going to be talking about reasoning tool use and agents. And so these are basically topics where we do chains of thought and kind of like intermediate steps, self-refine and self-correction methods. So these are methods where we go in and like correct the outputs, reasoning models, incorporating tools in inference. So this is like where you actually can make calls to external tools and do inference, and then agents and multi-agent communication. Next, we will talk about meta generation methods or ways to scale inference time compute by using generation as kind of like a subroutine. And so this includes minimum base risk and multi-sample strategies, reward models and best of n, re-ranking, how we build kind of language model systems, not models themselves, contrasting inference scaling and model size, and using external verifiers, as well as token budgets and training time distillation. And then finally, we're going to talk about kind of efficiency and system level optimization, like defining efficiency, library implementations and optimizations, KV cache optimization, draft models and speculative decoding, and ways to come up with alternative modeling strategies like MOE or sparse attention, other things like that. And then also probably transformer alternatives. What won't we cover? So we're going to talk in a very limited context about model training, only together with inference algorithms that these are training is used to optimize. We're not going to talk a whole lot about model architecture, only a very small amount. Not going to talk a whole lot about evaluation or reward models. And inference is basically going to be on text data. In terms of grading, 15% is going to be either quizzes or in-class participation. For in-class participation, because we really want to cover kind of like the cutting edge techniques that people are using, this actually wasn't written on the site, but we're going to ask everybody to give a short talk about a paper sometime during the semester. It's going to be about 5 minutes where you go and read a paper and introduce it on one of the topics we're going to talk about in the class. So that will be about 5% of the grade, and the other 10 will be like quizzes or small things like that. 60% is going to be the assignments. So there's going to be 3 of these total. And then 25% is going to be the final project. In terms of what the assignments, oh yeah, sorry. And so the assignments, I'll explain what they're going to look like in a second, but they're all going to be shared tasks. And we're going to have 3 tasks that we ask you to handle through inference. And we think this is interesting because they handle kind of different types of things people are doing with language models. And also they have different challenges for inference algorithms. So the first one is mathematical reasoning, very popular nowadays. So basically trying to solve math problems. The second one is multiple choice question answering. This is kind of interesting because your choices are very limited, but you can use latent variables like thinking to try to improve your accuracy. And also evaluation is very simple. And then the final one is open-ended generation. So this is like generating just text. And this is interesting because actually evaluation of it is tricky. And there's less reasoning that will go into it and maybe more like refining the output. Details to be released soon. This is a new class, so pardon our dust. Then the assignments, what they're going to look like is the first one's going to be on generation algorithms. We have the actual schedule on the site, but this is like roughly September, end of September. Meta generation algorithms. So this is, things like re-ranking or minimum base risk. And so this is going to be roughly end of October. Hardware and optimization, this is going to be roughly end of November. And then the final project, basically, we're going to ask you to put all of them together, and you get to be OpenAI and come up with your GPT, whatever. You can name it whatever you want. And you give us an API endpoint, and we hit your API endpoint and measure its latency, throughput, and accuracy. And so whichever one you're most excited about, you can optimize the most. So you can try to be the person who gets the most latency, the person who gets the best throughput, or the person who gets the best accuracy, but you can't be really bad at any of them. So that's basically the idea. And the idea is homework 1, 2, and 3 should give you a foundation to do the final project. So you shouldn't have to throw everything out. You can go and use the stuff that you did before. Great. That's all I have, but I realized I forgot the TA introduction slide, so I'd love to. Yeah, I did mention it. Yeah, sorry. I'd like to introduce our TAs and Amanda, who's the head TA and co-instructor. So if you guys can come up. Yeah, actually, I didn't introduce myself. I'm Graham. Nice to meet you. In particular, with respect to inference, I'm interested in reasoning. I'm interested in agents and tool use, and kind of things in that general direction. So those are kind of my specialties here. And then Amanda, if you want to.
I'm Amanda. I'm a fifth year PhD student. I work with Graham and with Matt Brumley from machine learning, and I'll be giving about half the lectures, so you'll be seeing a lot of me. I'm particularly interested in long context, in sort of scaling up inference time compute to accomplish different tasks, and in retrofitting or changing models to behave differently at inference time than they were originally trained to be.
Hi, my name is Vash Vishisht. I am a first year PhD student in LTI, figuring out my interests, but largely interested in making smaller models better. So whether it be from a compression angle or like from the training angle with synthetic data or distillation.
Hi guys, I'm Clara. I'm also a fifth year PhD student at LTI. I work on efficiency, so then inference has become more and more relevant to that side of things as well. Yeah.
Great. And yeah, and unfortunately, Shinran could not be here for good reasons, but he will be here next week and maybe give a self-introduction then. So that's all we have. The questions and discussion are up here. One other thing I forgot to mention is there's a poster presentation at the end of the course. It's going to be on December 2nd. So make sure you have that on your schedule and don't forget about it. All the other course policies are on the website. One thing I'd like to do now before everyone leaves is I talked about what we're going to talk about, and I would love feedback on what was missing, but you would like to hear more of. It might be that I just didn't mention it and we're already planning on handling it, but I'd love to hear things that people are interested in. Either now, we can also take them on Piazza, but anyone have questions or have any ideas of things you'd like to hear more about? Oh, yes, and there's going to be a quiz on Canvas, and that quiz for this class is basically going to be that feedback. So you can you can put it on the quiz, but if you want to raise your hand and talk about it now, happy to do that as well. Yeah.
Maybe a little bit about GPU basics. So you talked a little bit about how GPUs are not being utilized at the time of inference. That I clearly do not understand completely because what does that even mean?
Yep. Yeah, GPU basics. We have one class on hardware, so yes, we will do that. Yeah.
One is certain memories. I don't know if it's possible to have that in an assignment or.
Yeah, serving of MOEs. So for all of the assignments, we haven't completely worked this out, but I think what we want to do is we want to say you need to implement two things. And we will give maybe 2 to 3 recommended things. And then if you want to implement something else that's not in the recommended things, maybe you can have one free free thing where you can propose a thing that you implement. MOEs would be great for the efficiency portion, I think. But one thing I didn't mention is we are kind of like fixing the models that people are allowed to use for the last assignment. Because want everybody to be on on the same footing. And so I don't think at the moment we plan to have an MOE model there, just because it'd be more more work and more tricky. But yeah, that's great feedback. And we will talk about MOEs in one of the classes.
Second is that it's not completely obvious to me how requests are batched together. So it's like you're getting requests from multiple people at different amounts of time.
Yeah.
How is the request which can later inserted in the stream?
Yeah. So how requests are batched together, we're going to talk about that a little bit when we talk about libraries like the LLM and SGLang, because that's basically like one of the big innovations they have there. But yeah, we'll definitely cover that. Yeah.
Model size and how it like affects accuracy, and if that's a mode to increase inference speed and stuff like that.
Yeah, for sure. Model size, and I think we're going to talk about the trade-offs between spending time on using a big model versus spending time on like doing lots of rollouts and re-ranking them. So yeah, it's on the menu. Yeah. Is RAG going to be covered? RAG is probably not going to be covered, but we're going to be covering. Yeah, we're not going to be talking about embedding lookup really. Probably. Oh, okay, yeah, so we'll talk about it briefly in the systems.models thing, but yeah. Which search algorithm to pick for the problem? Yeah, hopefully we'll have lots of that in the first part. Yeah. Yeah.
How the reasoning models come up with the inference, what is going on in the backend? Is there in the lectures covered that?
What's going on with reasoning models? That's a good question. I wish I knew the answer to that question too. But we might talk about that a little bit in the reasoning models section, to the extent that anybody knows the answer to that. But yeah. Yes.
Will we cover topics like distillation?
We will talk about distillation. I don't think we're going to talk about pruning because that's more a model side thing, but maybe we could talk about it a little bit. We can see. Yeah. Yeah.
Or vision language model or like separate multi-coded language model other than text?
We're not going to talk about generation of stuff other than token sequences, which is usually text. For multimodal language models, I actually don't know if the decoder is the same. I don't know how much the inference process changes. It could, but it's not my specialty. So if you have anything in particular that you'd like to hear about it, happy to get the feedback. But, yeah. Okay. Yeah, thanks a lot, everyone. Great feedback, and we will see you on Thursday.